This is lesson 4.1, and obviously we are entering a new chapter at this point. You'll also notice that this lesson is about vectors. We are switching gears from matrices to vectors, though you'll see by the end of this lesson that we're going to kind of go full circle and recognize that vectors can be written or expressed as matrices. So we'll make that tie into what we've been doing the first few chapters, but now we're going to focus very specifically, like I said, on vectors. So to get started, let's just talk about what a vector is. We'll talk about some of the characteristics of a vector, get some vocabulary in things of that nature. So I'm going to put us into the XY coordinate plane, two-dimensional plane, and let's just talk about what a vector is. So a vector really is just anything that has direction and length, or what we call magnitude. Now, a lot of times what we like to do is in the coordinate system, we like to make these vectors in what we call component form. So I'm going to start with an initial point at the origin, and then I'm going to just extend a ray, it looks like a ray, out into, in this case, we'll go into the first quadrant, and we're going to end at a point called the terminal point. Now, sometimes you'll see that point in drawings, sometimes you won't. Sometimes you'll just see the arrow. But in either case, the tip of that arrow or where that point is simply the end of that vector. And so I'm going to call this vector u. We name vectors typically by lowercase letters. And in fact, in print, in text print, you'll see that a lot of times they'll actually bold that letter to show that it's a vector versus something else. That terminal point is at some fixed point. We'll just call this x1, x2. So in this case, vector u, like I said, has a length, which we will sometimes use the word magnitude to describe length, and it has direction. So unlike a ray that goes on forever, ray has an initial point, but a ray passes through a point and continues on into eternity in a particular direction. A vector has a very specified length. It ends at that terminal point or at the tip of the arrow, depending on kind of the drawing that you're looking at. And so together, that gives us a very specific figure. If I were to extend the length of that vector or change its direction, I have a completely different vector. As I mentioned, this vector is in what we call component form. And component form just simply means that we have the initial point at the origin. So the initial point at 0, 0. And then the components then are the coordinates of the terminal point. So the components are the coordinates of the terminal point. So that's what we call component form. Like I said, a vector does not have to start at the origin. A vector can start anywhere you want it to. It's useful, especially when we start applying mathematical operations, to put it in this position. All right, so last thing I want to just talk about as far as vectors go before we get into some of the math involved with this. Again, we can name vectors by a lowercase letter. So I'll, again, just continue to use u. A lot of times we use u, v, w, things like that, but you can use any letter. And we can also describe or write a vector in terms of that terminal point, again, especially when it's in component form. So I might describe it as being at the point x1, x2 with parentheses. This book in particular uses this notation of parentheses, but I've also seen it and personally kind of was taught under this notation of using angled brackets instead, and that's just to avoid confusion over a point. This is one of the things that's interesting about vectors is there does not seem to be a systematic universal symbology for vectors. I mentioned we see vectors listed as letters like u. You might sometimes see it as u with what looks like a ray symbol over it, but again, that can be confused with a ray. So you might also see it with a kind of a half arrow over it that looks like that. So there's all sorts of ways to represent vectors, and that can get confusing, and that's why context becomes very, very important in terms of understanding, is it a vector, is it an array, is it a point, what exactly are we dealing with here? But those are the important things to know about a vector, and just in terms of what it is, in terms of its characteristics. Obviously, we're going to get, as we get into the math and other uses of vectors, we'll build on this. One of the things about vectors, though, that I'll say is that vectors are very, very useful for anything that has, again, direction and length. So, a very common use of vectors is in force, where you might have objects pulling on two objects pulling on another object, and you want to know what is the result of those two objects acting on that third object. We can use vectors to very easily describe both by direction and in this case, the length representing the actual force or work being exerted, what happens to that object. And so we'll actually see some examples like that as we progress through some of the future lessons. All right, let's go ahead and move on, and let's talk about vector operations. So obviously we talked a lot about operations with matrices. We can add matrices, multiply by a scalar, all those sorts of things. And we can do some of those similar things with vectors, not all of them, and sometimes they look a little bit different. But let's start with just basic addition of two vectors. So if I want to add two vectors, I'm going to start by just showing this through a diagram. Again, I'm going to put two vectors in component form. So I'll have one vector. We'll put that here. We'll call this vector u. And then I'm just going to create another vector, and we'll call this vector v. So again, this could, for example, represent u and v being two objects acting on a third, which would be at the origin. And we want to know what is the result of those two u and v acting on that object. Adding two vectors together is really just figuring out what is the sum total of the horizontal and vertical components of those vectors. So in this case, let's suppose, for example, that u has its terminal point at u1 and u2, and v has its terminal point at v1, v2. If I want to add u plus v, I am simply going to add the first components, u1 and v1, and then I'm going to add the second components, u2 and v2. In this case, specifically because we're in two dimensions, representing a horizontal component and a vertical component. And that's how we'd add them together. If we had more terms, if we were in 3 dimensions or 4 dimensions or 5 dimensions, we would just do the same thing. We'd add the first components, add the second components, the third components, and so on. Obviously, if I had 3 or more vectors, we would just add all of the components in the same position together. All right. So in the diagram, what this actually represents is this idea that if I take v and I'm going to slide v up to basically a parallel position, but so that its tail, its initial point is at the terminal point of u. We call this tail to tip. This idea that we're moving one vector to the other, because if I add those two vectors together, the result is this vector right here. So this vector, and I'll try to bold this in a little bit darker. This vector is u plus v. And that would represent the combined actions of u and v together. Again, if this was an application of work or something like that. All right, so that's that. Let's just do an example just to really firm this up. Let's just suppose, for example, that we'll draw some vectors in here. Let's say I've got u that has its terminal point at 4, 1. And I don't know, I'll go down to the fourth quadrant this time. Let's put another vector down here, and let's put its terminal point at 2, -2. And again, we'll call this vector up in the first quadrant u. We'll call the other vector v. So if I want to add vector u plus v, again, I'm simply going to take the horizontal components, 4 plus 2, and the vertical components, 1 plus a -2, add those together, and my result is 6, -1. So again, if I were to take v and slide it up into a parallel position, and then draw in that resulting vector, that vector u plus v has its terminal point at 6, -1. All right, so that is addition. Let's go on and let's talk about scalar multiplication. So scalar multiplication is a lot like matrices. You know, if you have a matrix with a scalar, we just multiply all the entries by that scalar. Very, very similar with vectors. Let's just suppose that u is, 7, -2. Just make something up here. If I multiply it by a scalar, by 3, I am simply multiplying each of the components or each of the terms by 3, and that's going to give me a new vector 21, -6. The idea here being that if I have and I'll do a picture for a different vector, so this is not the one we just did, but if I have a vector u, and I was to multiply that by a value greater than 1, let's say I multiplied it by 3, that's going to take that vector and it's just going to make it 1, 2, 3 times as long. So that would be my new vector. Same direction, just 3 times longer. We're just increasing its length by a factor of 3. Obviously, if I multiply by less than 1, something between 0 and 1, I would shorten it. So if I multiplied it by half, I would have a vector that would be half as long. If I multiplied by a negative, it's going to push it in the exact opposite direction, 180 degrees in the other direction. So that would be if I multiplied by a negative constant. So that's scalar multiplication, pretty straightforward. By the way, I should mention, I meant to mention this earlier, but if I have a vector like 0, 0, we're just going to kind of stay in the 2 space right now. If I have a vector 0, 0, that is what we call the 0 vector. So anytime you have a vector where all of the values are 0, it's the 0 vector. All right, so let's go on then. And let's just kind of talk generally now. We've got some specifics in place now. Let's start to generalize some of these ideas. So basically, we've spent everything, all of our examples, everything we've been doing has been in 2 dimensions. All of those things apply no matter what dimension we're in. If we're in 2 dimensions, 1 dimension, 5 dimensions, 50 dimensions, it doesn't matter. How we add, how we multiply by a scalar, the concepts of what those are doing, all the same. All right. So if, for example, I have a vector x, we keep going as long as we want to. We can have x1, x2, x3, all the way up to xn. And just being however many dimensions we're dealing with. So specifically, if we're in 1 dimension, we just call this the 1 space. And this would be all real numbers. If it's r squared, we're in the 2 space or 2-dimensional space. And that would be all ordered pairs. So all ordered pairs in R, so again in real numbers. If I'm R3, I'm in the 3 space, so 3 dimensions, which would be all ordered triplets. I think you get the idea here. Again, staying in real numbers, and so on and so forth. And as we go to Rn, this would just be the n space, whatever n happens to be. And that's going to be all ordered n-tuples, again, in the real number system. Okay? So like I said, everything that we've applied before, the addition, the scalar multiplication, how we represent vectors, it's all the same. Obviously, we can't visually represent a vector beyond 3 dimensions, but again, the ideas apply. So in this case, just very, very simply, just do a quick, simple example. If I have a vector in the 4 space, maybe it's -2, 3, 1, 4, and I've got another vector in that same space, 7, 0, 9, -6. I can add those together by just adding all of the same position components. So I'd have -2 and 7 is 5, 3 and 0 is 3, 1 and 9 is 10, and 4 and -6 is -2. I could even take something like 3 times u minus 2 times v, and something like that would give me -6 minus 14 is negative 20. 9 minus 0 is 9. 3 minus 18 is negative 15. And 12 plus 12 would be 24. Okay, so you can combine, obviously, operations, do all those sorts of things. So in the book, it lists all the properties of vector addition and scalar multiplication, and this list should look very, very similar. It's something that we saw back with matrices, because again, a lot of the same conditions that apply for matrices also apply for vectors. So you've got a lot of different types of identities that involve addition. Down at the bottom, we've got the multiplication identities, things like that. So these are just all things that hold true for vectors, much like they held true for matrices. And similarly, obviously, if I'm going to add two vectors together, they have to be in the same n space, things like that. All right, so let's finish up by talking about linear combinations of vectors. So if I write a vector u as the sum of scalar multiples, as the sum of scalar multiples of vectors, we'll just call them v1, v2, up to vn, then basically what we're saying is we can take that vector u, so we're going to take vector u, we're going to write it as a sum of scalar multiples, that I'm able to write vector u as a constant times v1 plus a constant times v2 plus a constant times v3, and so on and so forth, up to a constant n times v sub n. Okay. So what exactly does this mean? Well, let's do an example to see what this is exactly saying. So let's suppose that we're going to take x to be a vector. We'll just call it -1, -2, and -2. We'll take another vector, and let's call that u, and we'll give that entries 0, 1, and 4. And let's take a vector v and write that as -1, 1, and 2. And then finally, let's make one more, and let's make w equal to 3, 1, 2. All right, and so all of these are obviously in the real number system and in the third space. So in the 3 space, again, real number system. What we're going to do is we're going to find scalars a, b, and c such that we can represent x, that first vector, as a scalar times u plus a scalar times v plus a scalar times w. Okay, so this is the idea of, where we said at the top that we can take vector u and write it as the sum of scalar multiples of other vectors. This is what we're saying. We've got a sum of 3 vectors, u, v, and w, multiplied by scalars, and that's going to give us this vector x. So to do this, again, just think about the fact that what we're really saying is x is -1, -2, -2. That's going to equal some scalar a times the vector u, which is 0, 1, 4, plus the scalar b times vector v, which is -1, 1, 2, and then plus some scalar times vector w, which is 3, 1, 2. Well, we know that if we're adding vectors together, we're going to add the first terms together. But in this case, those first terms are also being multiplied by scalars. So this -1, for example, in u is equal to a times 0, which is just 0, plus, I'm going to do this the other way. I'm going to put my 1 on the other side here. So -1 is going to be 0a minus b, and then plus 3c. And maybe you can already see where this is headed. Now I take my second term, negative 2. Well, negative 2 is the sum of a times 1, or just a, plus b times 1, or just b, and then plus c times 1, or just c. And then negative 2, again, that third position is just the sum of the third positions in our other vectors times their scalars. 4a plus 2b plus 2c. So we have a system of equations, takes us all the way back to chapter 1, a system of linear equations with 3 variables. And I won't go through the solving of this. Obviously, if we were to either use substitution, elimination, set up a matrix, however you'd want to solve this. If we solve this, we would find that A is 1, B is negative 2, and C is negative 1. So what that means then is that, again, looking back at this idea up here of how we want to represent x in terms of these other 3 variables, we can say that x is a times u, so 1 times u, or just u, and then minus 2 times v, and then minus 1 times negative 1 times w, or just minus w. Okay, so this is how we can take scalars of scalar multiplication with u, v, and w and use that to represent this other vector x. Now, I mentioned earlier that vectors can be written as matrices. And so in this case, if I want to write this idea as matrices, what we're really saying then is that u is equal to basically in this case we would say x, not u, x is equal to basically 0, 1, 4, because that's u, and then minus 2 times v, which is negative 1, 1, 2, and then minus w, which is 3, 1, 2. Because the position within a vector matches up to the position in other vectors, it's in the same way that matrices do, we're able to write it in this form with matrices. Okay, so that's kind of the idea behind how vectors and matrices tie together. Is we can think of a vector, that would be in this form just as a 1 column, or you could do it as a 1 row also matrix, either way, and represent the vectors in that fashion. So that wraps it up for this lesson. I really just want you to have an understanding of what vectors are, just some of the basic things that we can do with vectors. Make sure you understand how to add them, multiply them, do all those sorts of things. And then as we go forward in our next lesson, we're going to look at what are called vector spaces. We'll kind of get a little heady into some of the mathematics of just what it means to be a vector space and what qualifies, what disqualifies for that. And then eventually we'll get into some of the application and some of the deeper mathematics of vectors as we continue on in the course. So with that, I will see you in the next lesson.